All right, in this video, I'll be explaining a very typical work problem involving lifting a rope. All right, so this is taken from the Stewart Calculus textbook, 7th edition, number 13. But this is a very typical problem that you will likely see if you're taking a Calculus 2 class, or maybe even physics class, okay? What does it say? A heavy rope 50 feet long, weighs 0.5 foot per pound, and hangs over the edge of a building 120 feet high. How much work is done in pulling the rope to the top of the building? Okay, so what do we do in integral calculus? We always take slices. So we're going to slice up this rope into different lanes of dx. You can call it dy, whatever variable you want. I just happen to call it x here, okay? So what are we going to do with each slice? This is the representative slice, okay? Well, work is force times displacement, force times distance, whatever you want to memorize it as. So what is the force? It is the force due to gravity, which is weight. Okay, we have to connect all those concepts together. So what is the weight of this piece over here? Well, it tells us that it's 0.5 pounds per foot. dx is in feet. So it's just 0.5 dx. Look at the units, right? dx is in feet. This is foot per pound. So the feet cancel, pounds per foot, sorry. So the feet cancel and you're left with pounds. All right? So this piece has weight half dx. And what's the height? Well, if we set x equals 0 as the top of the building, then this piece is just x feet down. So it's a height of x, if you want to call it, okay? So you must lift it x feet. So you can think of it like that, okay? And x ranges from 0 to 50, the entire span of the rope. Okay, so the work is just integral from 0 to 50, force, 0.5 dx, times displacement, x. So 0.5x dx. And then we do fundamental theorem calculus, and you should get, I don't know why this didn't highlight, 625 feet times pounds, foot-pounds. Right? Now this is a very typical part B. How much work is done in pulling half the rope to the top of the building? Same scenario, but now we just want half the rope. So if we blindly set up this integral from 0 to 25, 0.5x dx, so what's this integral? Well, it's the same as part A, but I changed it to just 25. Let's see what happens. You'll get 156.25 foot-pounds. Okay? This integral is actually the work if the rope were 25 feet. So let me write that properly. Is the work done if the rope were 25 feet? Okay? So let's think about it. When you're lifting a rope from the top of the building, you can imagine the whole 50 feet is hanging off first, right? So it's going to be the heaviest. So as you start lifting it up, this is my second point here. As you start lifting it up, there's less hanging down. So it should be getting lighter and it should be getting easier, right? So the beginning portions of the rope should be taking the most work because the most is hanging down. There's the most weight hanging down. There's the most force due to gravity. All right? So the bottom portions of the rope should be the easiest and it should be taking less work because there's less weight hanging down. So does it make sense that half the rope is 156.25? We'll take 156, let's round 156 foot-pounds of work, and the whole rope took 625. This is just a fourth of 625. So it doesn't quite make sense, right? Remember, I was just saying the beginning parts of the rope should be the most work. It's the most hanging down. So it doesn't make sense that it's only a fourth. Okay. So what's the missing piece? Let's imagine this scenario. Let's imagine that the rope is 25 feet long. So this integral will be valid, right? And then let's just imagine the rest of the rope is just a hanging block of weight. What is that? What is that weight of that remaining 25 feet of rope? 25 times 0.5, that's 12.5 pounds. Okay, so as you're lifting that 25 feet of rope, you're constantly lifting 12.5 pounds as well from the other half of the rope. So we have to take that into account as well. So that's simple enough. It's just, again, force times displacement. force is 12 and a half. Displacement is we lifting it 25 feet. So 25, that's 312 and a half foot-pounds. So let's add these two numbers together, and you'll get 468.75 foot-pounds. Okay? And this makes a lot more sense now. And if we take the ratio from the whole rope, we realize that if we lift half the rope, it's 3/4 of the work needed for the entire rope. And this makes sense as I was explaining once again. The beginning portions should be the heaviest and takes the most work. There's the most hanging off. Okay, let's move on to the next one. This is very similar. Cable that weighs 2 pounds per foot, used to lift 800 pounds of coal up a mine shaft 500 feet deep. Find the work done. Okay, so let's sketch a scenario. It's very similar to that rope one I just did. That's why I'm doing this in the same video here. Okay, so here's the top of the mine shaft. You have this rope. You lifted that 800 pounds of coal 500 feet. So let's just say we have a 500-foot rope. Okay. So, like in the rope problem, we have to take into account the work needed to lift this 800 pounds of coal. So that's just 800 times 500, which is 400,000 foot-pounds. And now what about the cable itself? It takes work to lift it as well because it has some weight. So let's take a segment. It has a length of dx, so it has a weight of 2dx. Okay, and then we're lifting it x feet. So 2dx times x, that's 2x dx, and we integrate from 0 to 500 to the whole length of the rope. So then fundamental theory of calculus, you'll get 250, let me put a comma there, 1,000 foot-pounds. So you add the two together, the whole entire work needed is 650,000 foot-pounds. So hopefully this explains how this is a very typical problem. So hopefully my explanation helps explain why we have to do that integral and then add that additional number because we're lifting up this block of weight essentially.